Now let's take a look at our hexagonal crystal systems. So from this crystal, we can see that this direction, and this direction are equivalent. But when we index it using this A1, A2, Z, or the three axis indexing system, if we label this A, B, and C, the vector for A, this will become 0, 1, 0. For B, the direction is 1, 0, 0. And for C, we'll see here, this direction would be 1 bar, 1 bar, 0. So why is it 1 bar, 1 bar, 0? Because we need to project using these axes, and to get to this point, you need to add this direction here and this direction here to get this one. So it's adding, we're adding this one. This is along A1, and let's say this is along A2 to get the direction C. Now, even though directions A, B, C are crystallographically equivalent, in the three-axis system, their indices does not really readily tell us that they are equivalent, since it's 0, 1, 0, 1, 0, 0, and this one is 1 bar, 1 bar, 0. So crystallographers hated that. They didn't like that. They wanted a more convenient way to tell if directions would be the same. So what they did was they turned over to the four index system, or the four axis system, or we also call this the Miller-Bravais coordinate system. So in the Miller-Bravais coordinate system, again, we use four coordinate axes, A1, A2, and A3 are in the basal plane, and each of these has 120 degrees separation from each other. And we have a fourth axis here, the z-axis, which is perpendicular to A1, A2, and A3. So in the Miller-Bravais coordinate system, our directional indices are represented by this one, U, V, T, W, which corresponds to movements of the vector along A1, A2, A3, and Z, respectively. And we can convert from our three index system that we used for our other crystal structures before. So in this case, we'll denote the three index system as U prime, V prime, and W prime. So we can convert from U prime, V prime, W prime from the three axis system to the four axis system using the following conversions. So for U, our new U is equal to 1/3 2 times U prime minus V prime. For V, we have 1/3 2 times V prime minus U prime. For T, this is equal to negative U plus V. So it's not U prime V prime, but U plus V. And W is just equal to W prime. So now let's look back at our previous example where we had your vectors or our directions, A, B, and C. So capital A, capital B, and capital Z corresponding to the axis A1, A2, and A3. We know that these three have these indices in the three coordinate system. So what now if we convert them into the four coordinate system? We have U, V, T, and W. So for A, U prime is 0, and v prime is 1. So if we put this here, 2 times 0 minus 1, negative 1, times 1/3, have negative 1/3. For v, 2 times v, which is 1, 2 times 1, minus 0, this is 2 times 1/3, 2/3, and 40, negative u plus v, 2/3 plus minus 1/3 is equal to 1/3 negative. This will be equal to negative 1/3, and w is just equal to 0. So since these are all fractions, we make this the least integer that we can. Multiply this all by 3. We have 1 bar, 2, 1 bar, 0. For letter B, can you erase this one? For letter B, u prime is 1 and v prime is 0. U prime is 1, v prime is 0. 2 minus 0, 2 times 1/3, we have 2/3. 2 times 0 minus 1, negative 1 times 1/3, we have negative 1/3. And for this one, negative 1/3 plus 2/3 is 1/3, and negative of that is negative 1/3. And w is just 0. We will have, again, reduce this to integers or make this integers. We have 2, 1 bar, 1 bar, 0. And lastly, for the capital C direction, this one here, we have 1 bar, 1 bar for u prime and v prime respectively. So this is negative 1, negative 1. So 2 times negative 1, negative 2 minus negative 1. So negative 2 plus 1 have negative 1. This is negative 1/3. Same here. Negative 1, negative 1. So lang naman siya. We get negative 1/3 here. Then add negative 1/3 and negative 1/3 together. You get negative 2/3 here. Negative 1/3, negative 1/3. Add them. You get negative 2/3. But negate siya. So you have positive 2/3. And for w, that's just 0. Again, reduce this to, or become integers. For this one, have 1, 1, 2, 1 bar, 1 bar, 2, 0. 1 bar, 1 bar, 2, 0. And here, you can see that we're just arranging the indices. In this case, it is more apparent that vectors A, or the directions A, B, and C, are actually in a family. They are crystallographically equivalent directions. So now let's try a different example. Let's say we have this direction here. So this direction comes from this point here and terminates at this point here. So to get the index in the 4-coordinate system for this one, we first actually have to get the 3-coordinate index for this one. Well, basically, that's how I do things. So we need to get the 3-coordinate index for this one using A1, A2, and the z-axis. So essentially, we're looking for u prime, v prime, and w prime. And then we'll convert it to the u, v, t, w. So for this one, we'll just use the procedure that we used for the directions. So we get the tail and the head. The coordinates of our head is at, if we use A1, A2, and 0, Z, we have 0, 0, 1, because it's in the origin and projecting 1 unit above to get to the head. So the head coordinates is at 0, 0, 1. And for our tail, so to get to this point using this coordinate system, we have to move along 1 unit along A, and 1 unit along, 1 unit along A2 and 1 unit along A1 backwards. So the direction along A2 and A1 is 1, we have negative 1, and since it's in the basal plane, we didn't rise along Z, we have 0, tail. So to get u prime, v prime, and w prime, just use the head minus tail. So head minus tail, 0 minus -1, we have 1. Head minus tail, v 0 minus -1, have 1. And for w prime, 1 minus 0, we have 1. So in the 3-coordinate system, this is 1, 1, 1. So now we convert this to UVTW using these conversion formulas. U will be equal to 1/3 U prime V prime, 1/3 2 times 1 minus 1. This is 2 minus 1. 2 minus 1 is 1. We have 1/3 here. For V, this is 1/3 2 times 1 minus 1. We have 1/3 here. For T, this is negative U plus V, 1/3 plus 1/3. Negation of that one, we have negative 2/3. And for W, it's just the same as this one. This will be equal to 1. Then since this have thirds, we multiply all this by 3. QV TW will then be equal to 1, 1, 2 bar, 3. So in the 4-coordinate system, our direction, this direction here, has a coordinates of 1, 1, 2 bar, 3. Now let's say we want to do the opposite and we want to project a direction, but we are only given the coordinates or the index in the 4-axis system. So let's just use our previously known direction just for simplicity. Let's use 1, 1, 2 bar, 3. So to project this direction here, what we can do is we just trace along the specified A1, A2, A3, and Z. Since we know that U corresponds to A1, V corresponds to A2, T corresponds to A3, and W corresponds to movement along Z. So for A1, we move 1 unit along A1, 1 unit along A2, 2 units opposite direction of A3. So if A3 is going to this point, we're going 1, 2 directions to this point. Then we're moving 3 units upwards to Z. So 1, 2, 3. 1, 2, 3. And we'll see that will be, or we will have the same direction as we had before. So that's how you project your directions if you know the coordinates. Just follow your axis. So this is 1, 1, 2 bar, 3 direction. Now let's move on to indexing crystallographic planes in hexagonal crystal systems. So it is also convenient to represent planes in hexagonal crystals using our 4-index notation. So in this case, instead of UVTW, our planes are now expressed using HKIL. So this is similar to HKL in the 3-coordinate system, but we have I. But in contrast with our directions, it's much simpler to do for hexagonal crystals because essentially we just have the same H, K, and L as we had in our 3-coordinate system, with I being just a redundancy index where I is equal to negative H plus K. But the same rules apply to get crystallographic plates in the hexagonal crystal. So to illustrate this, let's look at an example. Now let's say we want to index this plane. Let's denote this plane as plane Q. So for plane Q, to get this plane, we just follow the same rules that we did for our planes in the 3-coordinate axis system or their Miller index. So first we look if the origin intersects this plane. It does not, so there's no need to move our origin. Then we get the intercepts with respect to A1, A2, and Z. So we ignore A3 for now. So the intercepts with respect to A1, the intersect, this is, let's say, 1. For A2, it's parallel. This plane is parallel to A2, so it'll be infinite. And for the Z axis, the intercept is also 1. Getting the reciprocals of this one, we get 1, 0, 1. So this will be our HKL, 1, 0, 1. To get the 4-coordinate system, we just have negative h plus k, this redundancy. We have 1, 0, negative 1 plus 0, which is equal to negative 1, 1 bar, 1. So this will be your plane in the 4-coordinate system, your Miller index in the 4-coordinate system. We can also actually consider A3. So if you consider A3, we can also get the intercept with respect to A3. So if we have A3 here, the intercept of this one is here. And this is negative 1. Reciprocal of that is negative 1. So A1 is 1, A2 is 0, A3 is 1 bar, and Z is 1. So we also have the same plane. And finally, let's say you want to draw a plane in our hexagonal crystal. So how would we do that? Let's say we have this plane here. We have 1, 1, 2 bar, 0. So to draw this plane, we just use the same method that we did for our Miller index in 3 dimensions. So from here, since we know this is the reciprocal of the intercepts, we reciprocal each of this for this is A1, A2, A3, and Z. Reciprocal of this one is 1, 1. 2 bar, negative 2, reciprocal is negative 1/2, and reciprocal of 0. If 0, the index is 0, this will mean that it's parallel to the Z direction, it's infinity. Then we just draw a plane that has intercepts of 1 at A1, 1 at A2, negative 1/2 at A3, and at Z it is parallel. So A1, let's say 1, this is, say, this plane. For A2, the intercept is this plane. For A3, 1/2. So if this is 1, it's around here. So I can draw a straight line to save my life. Get the line tool. It's this one. Then since this plane is parallel with Z, so it will be this plane. So this plane is our 1, 1, 2 bar, 0 plane.